What is our upcoming schedule? So, Unit 3 started last week. When did it end? Next week. 3 lectures, probably 4 weeks of material. Are you doing that? Yeah, it's a true thing. So that the problem is, if we expand the time on that, we have to cut it somewhere. And what I'm hoping is that the foundation that you've established in how to approach, think about the concepts and the equations in Unit 1, taking that approach and applying to equilibrium in Unit 2, and has provided a solid enough foundation that you can raise through Unit 3. However, it is vitally important that you get your questions answered as soon as possible. So find help, go to the Chem 106 lab in Provo, come to office hours, let's get this stuff worked out for you. This is the stage of the semester where you start to get tired, right? Yeah, that happens. Okay, can you tell yourself that if you steel yourself to really focus and burn through this material for 2 weeks, you can have a break? You can't. We don't actually have anything other than a single smart work due the week, which is nice. Okay. I need my little clicker here. Also work. Starting now, there is extra pre-recorded material available. So if you go to the content section of Learning Suite, you're used to going there, I hope, or where it says first PowerPoint slides. There's also a section, if you haven't noticed it, called pre-recorded lecture snips. Some of that is just links to Professor Dave and other people giving cogent explanations of material. But there are also some recordings of me going over the material. And that's starting in lecture 10. There's a bunch of it for 11, a bunch of it for 12 and 13 lectures. Okay. Review here. Tell your neighbor what a Bronsted-Lowry acid-base reaction is and how you would recognize it. What I'm asking you to do is tell them what you are convinced is on the slide before you look at it. Okay, when we're looking at acid-base reactions, we're tracking an H+ that moves from an acid to a base. And we track that with the formula. How would we recognize it if the equation was just written out with the formula? H goes away on the starting material side, shows up in a different location in the products, right? It's a proton, so what happens to the charge? The molecule that loses, so if we look at this reaction from the formula, is A a real acid? It's a real thing. No, it's a formula that stands in for the acid. So the HA, this A could be chlorine or fluorine or bromine or hydrogen sulfate, it could be any number of things, right? We look at the formula, this molecular structure becomes A-, when H+ left it. And base, here we're denoting as B-. What would the base have to act as a base? Often it has a negative charge. It doesn't have to. What does it have to have? Pair. Okay, because the lone pair is going to service the electrons that become the bond to the H+. Okay, so terminology that you need to know, you need to be able to recognize the acid and the base on the starting material side. Also need to know that when the acid loses its proton, it becomes conjugate base on the other side of the reaction. Why is it? Well, back up a little bit. When the base gains a proton, it becomes the conjugate acid. Why do we use that terminology?
Because in the reverse reaction, the molecule that can give the proton is different.
Right, if we run the reaction backwards, so this is a reaction that has a specific equilibrium, right? And you know that the equilibrium comes because of the balance of the forward and backwards reaction. If we're running this reaction backwards, then the conjugate base accepts the proton to form the acid. The conjugate acid is what donates or gives up the proton. Okay. Most of last class, we talked about just the reaction, a specific kind of Bronsted-Lowry acid-base reaction that happens when you take an acid or a base and mix it into water. And when you take an acid and mix it into water, what it does is donate its proton to the water. So in an aqueous solution of an acid, the base that's acting is the water itself, and we form the conjugate base of the acid and hydronium ion. Okay. One thing to keep in mind about acid-base reactions is that sometimes when we add something, there's a sodium or potassium, there's counter ions in the formula. Most of the time, they're not actually involved in the acid-base reaction. We call them spectator ions. So often we can just leave them out. Okay, one thing that confuses students is that chemists use a bunch of different language and a bunch of different notations when they're talking about acid-base reactions. And often, have you noticed that chemists like to choose whatever is shortest to write? Often, we use a notation that comes from a not very modern model for acid-base reactions. And that's the Arrhenius model, introduced by who? Ben Arrhenius, who's also famous for the Arrhenius equation, right? There's a family in my ward whose last name is Arrhenius. When they moved in, I got so excited because of their last name, but that isn't the sort of thing you can tell someone. Oh, cool. You have the same name as one of my favorite equations. In a sign of how small the world is, Sister Arrhenius's parents live next door to my parents in a small town in southern Alberta. So we're not just connected by Sven Arrhenius. Okay, so Arrhenius said, when you dissolve an acid in water, it produces what he called H+. So the language that Arrhenius used, he said, an acid dissociates in water or comes apart by giving up the proton. The acid gives up the proton to form what we now would call the conjugate base. And he called it floating protons. Is that really what's happening? What's really happening? Where's that floating proton associated with? Yeah, it's associated with water. So when we write H+, according to the Arrhenius model, it's more accurate to say what's really happening is that we're forming hydronium ion, H3O+. Okay, but you have, I'm certain, already seen that when you look online for acid-base stuff, when you want to see appropriate Bronsted-Lowry notation, very often what you see is Arrhenius notation with an H+. And it's okay to use that as long as you know that that's not the real thing. Okay, so Arrhenius said we can categorize acids in terms of them being a strong acid or a weak acid. Now, in acid-base language, strong or weak just refers to where the equilibrium for this reaction lies. So Arrhenius said a strong acid dissociates completely. So what does that mean in terms of Unit 2 language? Equilibrium lies very far to the right. So when Arrhenius said completely, he means very far to the right. What kind of K values would we be talking about? Greater than 1. Most of them greater than 10. Some of them hugely greater, like 10 to the 23rd. Okay, in Unit 2, language and thinking, what kinds of delta G naught values would correspond to a strong acid and which would correspond to a weak acid? So if a strong acid dissociates completely, equilibrium lies on the side of product, what's the sign of delta G naught that goes with that? Negative. Okay, so if a weak acid, the equilibrium lies on the side of the starting materials or on the left, what's the sign of delta G naught that would go with? Positive, yeah. Okay. So a strong acid equilibrium lies completely to the right, a weak acid equilibrium lies to the left. Now, Arrhenius also talked about strong bases and weak bases. Not on the slide. When we add a base to water, what happens? So if an acid reacts with water to donate the proton to water, what does the base do? It reacts with the water to take a proton from water to produce hydroxide. That notation, strong versus weak, does that still apply though? A strong base, when it reacts with water, where does the equilibrium lie? All the way on the side of product. A weak base, the left on the side of reactants. Yeah. Okay.
I don't think your voice is actually going through your microphone. I think it's just kind of going against your shirt a little bit. We can hear
Something's
it.
not working because it's. Let's try this. Is that better?
We'll kind of just,
No. Making a lot of. See if there's anyone online. Melissa, can you hear me through the microphone? Weird. All right. The other microphone. Problem is the other microphone doesn't currently have batteries. That was for me before. So I couldn't do the batteries.
I think the base is on.
Okay, so an acid-base reaction involves an H plus that's transferred from one reaction. Oh, how could I give you the actual battery? I handed you the microphone. I'm so sorry. One is real, just so you know. Okay. There's lots of molecules that have hydrogens, right? So how do you know which of the hydrogens is going to be transferred? Can any of them be transferred? How do you tell? Okay, sharing the recipe. Is that better? Maybe. It sounds better in my ears, but okay. See what we can do here. Let me draw you a picture. Let me draw you a complicated, fairly complicated molecule. And I'm just making it up as I go. All right, lots of different hydrogens, right? I'm gonna just change the camera angle here. Okay. Are all of the hydrogens the same kind of hydrogen? Are they gonna react the same? Are they gonna behave the same? They're not. Depending on what they're bonded to, they're going to behave differently. So these three hydrogens on this end, they're all pretty much the same. They're all hydrogens on a methyl group. This is a different hydrogen. Hydrogen on the alcohol group on the OH is also a different hydrogen. Here's another kind of hydrogen. Here's another kind of hydrogen. Here's another kind of hydrogen. Can we look at the structure of that molecule and figure out what's going to be the most acidic hydrogen? We could in fact rank the hydrogens or the protons in terms of what is easiest to pull off or to be donated, and what's hardest. Okay, how do we do that? There's a principle here. The acidity of a proton depends on how stable the structure is that forms when we pull that proton off. Okay, so what we have to do here is figure out what the structure of the conjugate base would be when we pull off each proton. Rank those stabilities in terms of electronegativity of the atom that bears the charge, any possible resonance, induction, any number of things. And if we can rank the stability of the conjugate bases, then we can figure out what the stability of the initial protons is. Okay, so if we pull off proton A, what's going to happen to the electrons in the bond? Because we're pulling the nucleus away without its proton, without its electron. So what happens? Yeah, the two electrons that were in the bond are left behind, so they form a lone pair. Form this structure. Now, what makes the conjugate base stable or unstable depends on the potential energy of the charge that forms typically. Okay, so now we have a charge on carbon. What do we know about the electronegativity of carbon? It's not very electronegative, right? How can we tell from the periodic table? What are the trends in the periodic table? Okay, as you go across a row, what happens to the electronegativity? It goes up. As you go down a column, what happens? Electronegativity goes down. So carbon is not very far to the right on the periodic table. It's not very electronegative. If it's not very electronegative, that means it doesn't have very much attraction for electrons, right? So what happens to the stability if you try to give it extra electrons and a negative charge? It doesn't handle that very well. Stability goes down. What happens to potential energy? It goes up. Okay, if the potential energy goes up, how hard is it to create this? It's pretty hard. So are we going to pull off hydrogen A easily? No, we're not. Okay, how about hydrogen B? If we form hydrogen B, we're going to pull off that proton. It will leave behind a lone pair on another carbon. Talk to me about the stability of the lone pair and the negative charge on this carbon. As always, a negative charge on a carbon is not going to be very stable, right? So this is going to be a fairly high potential energy structure. It's going to be hard to accomplish that, hard to form it. So we're not that likely to pull off hydrogen B. Is the acidity of hydrogen A and hydrogen B the same? How do we answer that? You have to say, well, is the stability of the conjugate base here and the conjugate base here the same? Are they identical? Okay, Cole, why aren't they identical? Yeah, this OH on the top is going to do something. Talk to me about the bond polarity between the carbon and the oxygen here. Look at that. Go back to unit 2 in Chem 105 where you talked about bond polarity. If you have a highly electronegative atom like oxygen bonded to a carbon, what does it do to the electrons in that bond? It shifts it towards the more electronegative atom. We could draw a little bond dipole like this. So it's pulling electrons towards the hydroxide. What does that do to the negative charge on the carbon? It pulls some of it away. Organic chemists would say it minimizes the charge on the carbon. Okay, so if we're minimizing the charge on the carbon by the bond dipole with the OH there, what does it do to the stability of that negative charge? Stability goes up, what happens to potential energy? It goes down, so what happens to how easy is it is to form this carbanion as opposed to the original one? It's easier to form it, so what does that say about the stability of hydrogen B? Or I should say not stability, the acidity of hydrogen B. It's more acidic, right? So if we're ranking, we can say hydrogen A is less, or proton A is less acidic than proton B, right? All right. How about proton D?
Just a quick question. So would like sterics and like, let's say like a hydrocarbon, like if there's a bunch of other atoms around it, would that affect anything in terms of acidity?
Potentially.
Like would it protect it from being like cleaved off or donated?
Proton's pretty small, so mostly sterics isn't gonna make it. It could for other things, but not necessarily for this. All right. We have 4 protons left. B, E, and F. Which one do you think is going to be the least acidic? Prediction here. Okay, people are saying D. Why would proton D be less acidic than E, C, E, and F? When you pull the proton off, you pull proton D off, where does the negative charge get left? Carbon. If you pull proton C off, where does the negative charge get left? Oxygen. Pull E off, nitrogen. Pull F off, oxygen. Okay, so in this case, we have different atoms that the negative charge can be left on. That's where the rule of the electronegativity of the atom bearing the charge matters. Okay, we're comparing those. Actually, I'm going to do this. If we pull off, if I actually wrote my structure correctly, wouldn't it? Okay, if we pull off hydrogen B. See, I don't even want to do hydrogen B because I'm not sure I can rank it perfectly versus hydrogen B. But hydrogen D, that's the same as hydrogen B. It doesn't have as many nitrogen pulling on it. It doesn't pull as strongly as the oxygen. But you have the other oxygens pulling kind of on either side of it, so it could be about the same. We're not even going to rank it because I will only give you things to rank that are fairly clear cut, and this is not it. Okay, let's do hydrogen E. If we pull off or donate proton E. Let's do C first. How's that? Talk to me about the negative charge here. In general, can oxygen handle a negative charge? Yes. Does oxygen like a negative charge? Is it going to stabilize or destabilize the molecule if we have a negative charge on the oxygen compared to the proton on the oxygen? It's going to destabilize it, right? But it's not going to destabilize it hugely. Okay, so what do we know about proton C? More stable than proton B, right? Okay. If we pull off protein E, we're pulling off a proton T. In science, it matters whether you're saying a proton or a protein. So I'm trying to say proton here. If we pull off proton E, where's the negative charge going to be?
Nitrogen.
It's going to be left on a nitrogen. Nitrogen had 1 lone pair before. If we pull off a proton, we have 2 lone pairs. And what else? Negative charge. Okay, talk to me about a negative charge on nitrogen. It's not as good as oxygen, but compare it to the negative charge on the carbon. It's better than carbon. So what does that mean about the acidity of this proton? more acidic than proton A, but less acidic than proton C. We're gonna do this. All right, we have one final one left, right?
So for proton B, you pull off the proton, the negative charge is left on the carbon,
Uh-huh.
and the oxygen is polarized
Oxygen stabilizes it somewhat.
somewhat, but since the negative charge is left on a carbon instead of a nitrogen, proton B is more stable.
Okay, so the most important thing is what kind of atom is the negative charge left on? That trumps everything else. And if you can have a negative charge on oxygen versus nitrogen versus carbon, it's going to be the negative charge left on oxygen that happens. Okay. However, we have another example here. Hydrogen F, or the proton F. If we pull that one off, where's the negative charge? It's on an oxygen. If we pull that proton off, we take the electrons that were forming the bond to the hydrogen and we leave those electrons behind on the oxygen. So now we have a negative charge to oxygen, on oxygen. Okay, but we also had a negative charge on oxygen when we pulled this proton off. So how do we decide? Okay, we look for things that can stabilize a negative charge. One of them is induction. You could argue that there's some induction here because this is a polar bond, right? Pulling some of the negative charge away. But what else do we have here? All of those carboxylic acids, anything with a COOH group or a CO2H, UKA table, all of them can do resonance. Okay, and in resonance, what we do when we draw resonance structures is we're essentially just moving the electrons around. So we take a lone pair to make a double bond. The pi bond in our double bond becomes a lone pair on the oxygen. Just a little 105 reminder. If I draw two resonance structures, does that mean the molecule is flipping back and forth between them? Josh is shaking his head wide in the back. Do you want to elaborate?
It would be more like the electrons are shared in a cloud between the two, like oxygens, or like, I guess kind of like, yeah, it's like a shared domain.
Yeah. What actually happens, resonance structures are what we use to make Lewis structures more accurate. But Lewis structures have a fundamental problem. They're assuming that the electrons are little dots, right? What do we actually know about electrons? It's an electron cloud that inhabits a space that we call an orbital, right? If you draw a valence bond theory hybrid orbital representation of this molecule, you end up with p orbitals on all of the oxygen, carbon, and oxygen. And those p orbitals are all mixing together. And the mixed picture represents both of the resonance structures. Another way to say that is the actual molecule looks like both resonance structures at once. Okay, so what does that mean? Is the negative charge on only a single oxygen? Negative charge is spread out between two oxygens so that each oxygen only has part of a charge. What happens to the stability when we don't have a whole charge anywhere? Stability goes up. What happens to potential energy? Potential energy decreases. What happens to how hard it is to pull off the proton to make that structure?
It's easier.
It's easier. Yeah, it's easier to do. Okay, so what's the most acidic proton on this structure? HF. Okay, and it's HF. Oxygen's negative charge. HC has an oxygen negative charge. It has plus resonance stabilization. Okay. He has nitrogen negative charge. This has a carbon negative charge. Plus conduction, stabilize it. Has a carbon negative charge. Anything stabilizing it? Okay. So the rules are, what's the most important thing that you look for? Negative charges on an electronegative atom in the conjugate base. That's the most important thing. So if you're ranking acidities, you draw all the conjugate bases out and you choose the one that, first of all, has the negative charge on the most electronegative atom. Allie.
Just real quick review question. Is that what induction means?
Induction is stabilization because of polar bonds bonded to or close to the negative charge in the base. Okay. Ben.
So does, where the negative charge is trumps all else.
So where the negative charge is trumps all else. Way to say it.
And the follow-up, so is like resonance
Yeah.
more powerful than induction?
Okay. And then Ben says, and is resonance more powerful than induction? Yes. It is. Okay. There's one other thing that smart work loves to talk about. It's the size of the atom bearing the charge. Okay. The most important thing is what kind of atom has a negative charge in the conjugate base. That's the most important thing. And in nearly every case, we choose the negative charge on the most electronegative atom. And then if that's resonance stabilized too, that's great. Makes a huge difference. Okay, there's a couple of kind of funny exceptions. If we go to the periodic table here, what if the negative charge on the conjugate base is on oxygen versus on sulfur? Normally, we would say oxygen is more electronegative than sulfur, so it's better to have the negative charge on the oxygen. But when the atoms that have the negative charge are in the same family, we don't choose the most electronegative one, we choose the larger one, which is which one? Sulfur. We see that in, specifically in the acids of acid halides. So hydrofluoric acid versus hydrochloric acid versus hydrochloric acid versus hydroiodic acid. The order of those acidities. When the halogen is lower on the periodic table, the acid halide is actually stronger. That's another example. If you pull off the proton, here, let me draw it for those. Black works better for. Okay, when we pull off the proton, what are the conjugate bases that form? Each of the conjugate bases that form are just the electron. And we know that because the negative charge is on different atoms in the conjugate base, it's the stability of that atom that's going to make a difference. That's important, right? Okay. Normally, we would say when we're comparing the stability of the conjugate bases, the first thing we look for is the electronegativity. The most electronegative atom is going to have the highest stability, which makes the precursor acid the most acidic. However, fluorine, chlorine, bromine, and iodine are all in the same column of the periodic table. So what analysis do we use here? We use size. Why does that make a difference? Okay, iodine, as you go down the periodic table, there's higher and higher energy levels, which means the electron cloud gets bigger and bigger. What does that do to the stability of the charge? It spreads it out, just like resonance increases stability by spreading out the charge. When you take a negative charge and you spread it out over a larger atom, you're essentially deconcentrating or diluting the charge, which makes it more stable. Fluoride is pretty small, it's really teeny. And so the negative charge in fluoride is compressed into a very small space. That's not very stable. So what happens to the acidity of hydrogen fluoride? Hydrogen fluoride is actually a weak acid, where all the other ones are strong. Okay, that was probably longer than any of you wanted to spend on that. Perhaps helpful. Okay. Really what we're saying is examine the stability of the negative charge in the conjugate base and everything that can affect it. The more stable the conjugate base, what happens to the acidity of that proton? Goes up, which is another way of saying the acidity of the conjugate acid goes up. Okay, we talked about those. Now, it'd be nice if you had some way to check your assumptions about what was more or less acidic, right? Fortunately for all of us, chemists love tables. Yeah. So there are huge quantities of data about acids. Right? Sometimes we express the Ka values a different way. We express them as pKa's, which is the minus log of the Ka values. Okay, so the Ka tables all are based on the reaction of that acid with water. So you take the acid, react it with water to form conjugate base and hydrogen. And we have equilibrium constants for that reaction for huge numbers of acids. We call the equilibrium constant Ka, and all the unit 2 trends apply. So the higher the Ka, what happens to the equilibrium? Farther to the right. So what does that mean about the strength of the acid? Stronger, yeah. Okay. So pretty much the bigger the Ka, the stronger the acid. Where's the dividing line between weak and strong acids? Thing with the Ka greater than 1 counts as a strong acid. Functionally, I've never met a strong acid that didn't have a Ka of at least 10. There just isn't a lot of stuff that clusters around it. Yes.
On the Ka table, isn't it like above or below hydronium?
Yes. Yeah. Okay, we can also express the Kas as pKas. Tell your neighbor how mathematically you know what the pK values for a strong or weak acid. So without memorizing them, how can you just think it through to analyze what pK values correspond to a strong acid versus a weak acid?
Dissociates, it's gonna be fine.
The lower.
So a base 10 log, what the log really does is pull out what the exponent is. essentially.
Yeah.
So if I have a large Ka value, what's the sign of my exponents, positive or negative? So large Ka would have a value less than 1, which means probably an exponent that is positive, right? Large number. Okay, if you take the minus of a positive exponent and take the log of it, you're going to get a negative one. So strong, have to think through the math there. Strong acids have a negative pK value. Weak acids have a positive pK value. Okay, the weaker the acid, what happens to the pK value? The more positive it gets. If we go back to that, our evaluation of the acidities of different protons, if you have methane, for example, CH4, and you try to pull one of those protons off, not very acidic, right? Ka value is on the scale of 10 to the 48. This makes the pK positive 48. Okay, we have these tables of values. Tell your neighbor where to find strong acids and weak acids, and what are the trends in acidity and base strength on the table.
Strong acid first.
So this line here with hydronium, what would the K value be if it were reported here? Hydronium plus water produces water plus hydronium. So what does the K value have to be? It has to be 1 because you have the same things, same entities in the numerator denominator. This is back to K value of 1. Okay, so as you go up the table, what happens to acid strength? The stronger acids above this line get stronger and stronger as you go up. The weak acids are below that line, right? What happens to their strength as you go down? Okay, the conjugate bases are listed over here. What happens to the strength of the conjugate bases? As the acid strength gets weaker, what happens to the conjugate base strength? It goes strong, it gets stronger. Okay, these bases, the conjugate bases of strong acids, are they a strong enough base to do anything in aqueous solution? They don't even react in aqueous solution, they just sit there, which is why the equilibrium lies far to the right and why those are all strong acids. Okay, as you go down the table, what happens to your base strength? It gets stronger. So all of these conjugate bases of weak acids, each of those bases is strong enough to react with water by itself. If we take any of the conjugate bases on this table and add them to a solution of water to make a solution of that base in water, all of these bases will react with water to form hydroxide. Okay. These are all, strictly speaking, still called weak bases. How come? What's the definition of a weak base?
Associate.
Okay, Arrhenius would say a weak base is one that doesn't dissociate completely with water. In equilibrium speak, what that means is each of these weak bases, when you form a solution with them in water, they will react with water, but equilibrium will still lie on the left. So the Kb values for reaction of those bases with water are still all less than 1. Okay, we also have a category called strong base. Arrhenius said a strong base, when you mix it with water, equilibrium lies all the way to the right on the side of product to produce hydroxide. Are there any strong bases on that table? Strong bases are the conjugate bases, acids with equilibrium constants, Ka values less than 10 to the minus 14. Actually not any. Okay, so we have this Kb value, right? Tell your neighbor what kind of Kb values a base would have, a strong base and a weak base. What Ka and Kb values that would correspond to for their conjugate acid. Remember, acid strength and conjugate base strength are related, right? So that means Kb values have to be related to the Ka values of their conjugate acids. A lot of kind of crinkled brows here. It's a lot of connections, right? So go back to the table here. Base strength, the conjugate base strength is related to the strength of the conjugate acid, right? So the base strength is related to the Ka value. Does that mean the conjugate base strength is also related to the pKa value? It is, because those are just different ways to say the same thing, right? So when we're analyzing just the bases and the reaction with water, we can analyze them with Kb values and Kb values, but are you necessarily going to have a Kb table on the exam? No, what you get is a Ka table. So you have to be able to figure out what the base strength is from how strong an acid the conjugate base or conjugate acid of the bases of the pairing. Okay, if you are given the Kb, the stronger the Kb, the higher the Kb, the stronger the base, right? Which means what about the pKb? Stronger the base, the higher the Kb, and the more positive the pKb. That's also the trend for Ka values. I'll let you go home and chart that all out because it's a lot of things to hold in your head at once. You should be able to connect the strength of a base by treating it as the conjugate base in an acid-base reaction and looking up the values on the Ka table. Okay, because acid and conjugate base strength are related in aqueous solution via the Ka and Kb values, then for every acid and its conjugate base, if you multiply the equilibrium constant, the Ka value for the acid, times the Kb for its conjugate base, you will always end up with a single number, which is what? 1 times 10 to the minus 14th. So if I go back to the Ka table, if I have the Ka value for benzoic acid, for example, is it an easy task to calculate the Kb value for its conjugate base, benzoate? How would you do it? pKb always equals the Kw divided by the Ka for the conjugate acid. So those ideas are paired. Okay. Since Ka and Kb can be expressed as a pKa and a pKb, the same relationship here is expressed in log form by adding. At 14, yes.
KW always 1 times 10 to the negative 14th.
At 25 degrees Celsius, Kw is always 1 times 10 to the minus 14th. And we don't discuss or show you any other data for acid-base reactions other than at 25 degrees. We go back to the table. Will those Ka values be correct at a different temperature? No, they won't. How come? They're equilibrium constants, and equilibrium constants change when you change the temperature. Most of these reactions have a positive delta H naught value. Sorry, I lied. Negative delta H naught value. If they have a negative delta H naught value, what will happen to the Kas as you change the temperature? Remember? So negative delta H naught values mean it's an exothermic reaction. If you increase the temperature, which side of the reaction are you selectively stressing? Products. So what happens to the equilibrium? Shifts towards starting material. What will happen to the K values? They'll go down. Yes.
I don't want to derail the conversation. I was just wondering what the difference in the strengths of like strong acids are if we accept that like at equilibrium, their concentration, their initial concentration will represent like the hydronium ion concentration. So it's like, I don't know if my question makes sense.
It does make sense. Okay, here's a contradiction. We told you in unit 2 that if it's at equilibrium, you're always going to have some starting material and some product present, right? And yet Iranian said strong acids dissociate completely. Is that a contradiction? It is. Is it a contradiction in the context of the significant figures that we typically are bound by? Okay, nitric acid, it has a pretty small strong acid Ka. It's only about 25. Okay, but all the rest of them, they're 1,000 and greater. If your K value is 1,000, how much starting material do you have left? Almost none. Within the significant figures of the concentrations that we're using, do we care about the almost none? No. And so we use the verbiage completely dissociated. Is that actually factually inappropriate to use that word? Nothing dissociates completely. It's still governed by equilibrium principles, right? But within the limits of the significant figures, it might as well be completely, and life is easier if we can make the assumption that it dissociates completely. So we do. We like easy. Okay, so you can tell your neighbor, what is a strong acid? Define equilibrium, Ka, complete versus incomplete dissociation, and what kind of Ka values would you get? I would say it ionizes completely, equilibrium lies to the right, far to the right, which would correspond to a negative delta G naught value. That would be a Ka value. Well, Also, that means the conjugate base can't really back react very well, right? So one definition of a strong acid is that its conjugate base is unreactive. Okay, that would correspond to a Ka much greater than 1 and a negative pKa value. How about a weak acid? Doesn't dissociate completely. Equilibrium lies to the left. What about the reactivity of its conjugate base? It has to be somewhat reactive because it has to react enough to force the equilibrium back to the left. What do we know about its Ka values? Less than 1, pK values are positive. Okay, strong base. When you mix a strong base into water, equilibrium lies to the right to produce hydroxide. What does that say about the conjugate base of a strong base? Conjugate acid of a strong base. Yeah, conjugate acid is very weak. How about a weak base? A weak base is the conjugate base of a weak acid. Some reactivity with water. Equilibrium probably still lies on the left. So AB values are less than 1, which means the conjugate acid has a Ka value also less than 1. Calculate what the AB values are. Okay. Let's see. Okay, keep in mind, we talked about water. Let's go back to this concept that water can be an acid or a base. We know that is because when we add an acid to water, what does the water do? Yeah, it's like a base. But when we add a base to water, what does the water do? It's like an acid. Water doesn't take a very firm stand, does it? Okay, so we have this reaction that's always going on in water. And that reaction that's always going on in water means that the hydronium concentration and the hydroxide concentration in solution in water at one time, one is always going to affect the other. And if I add a bunch of acid, if I add a bunch of acid to water, what's that going to do to this equilibrium? If I add acid to water, what's the acid going to make in water? We make hydronium. So what happens to this concentration? It goes up. So what happens to this reaction? It shifts back. Is this an example of the common ion effect? Yeah, we use the common ion effect to talk about solubility, but when we're talking about acid-base reactions, hydronium is a common ion. Two equilibria going on. The acid that we add and this water autoionization. Okay, so if we add acid to the solution, we're increasing the hydronium ion concentration, which stresses the product, which does what? Pushes it back towards the side of starting material for this reaction. This does what to our hydroxide concentration? The increase in hydronium makes hydroxide concentration go down. If we add base to water, it's going to increase the hydroxide concentration. So what does that do to the hydronium concentration? Makes it go down. And we can know what the concentration of each will be. If we know the concentration of hydroxide, we can calculate the concentration of hydrogen and vice versa. Okay, use the there are some conversions that you need to be able to do that we talked about last time. You need to be able to convert hydronium to pH, pH to POH, POH to hydroxide concentration. What do we need to do? You need to be able to convert Ka to pKa. We need to be able to get the Kb or base from K of the conjugate acid. Wow. Okay. Students commonly struggle with what's the difference between pH and pKa?
pH has to do with the solution. pKa is only the acid itself.
Yeah, pKa is just another way of reporting Ka. So it just tells you how strong the acid is that you're dealing with. But pH tells you how much hydronium do you actually have in that solution, which is a function both of the Ka, the strength of the acid, and how much acid you have. So pH applies to a single solution. What does pKa apply to? A single kind of acid, which could be found in multiple different solutions, right? Okay. In Unit 3, we apply all of the equilibrium calculations that you've had to do to acid-base reactions. The only real difference between what we did before and what we do now is that we don't ever ask you to report the hydronium concentration. What do we ask you to report? pH. Yeah. These are all versions of the kinds of reactions you've already done with the extra layer that the concentrations of hydronium or hydroxide are reported as pH of PO. And we have a couple extra complications today. We're going to do titrations, and we're going to talk about polyprotic acids. Actually, aren't. Okay, so everything that we've done before applies. We have different terms like pH. It's really just the same thing. So your task is to take what you know in Unit 2 and just carefully convert what we're learning in Unit 3 and translate it into what you already know. Okay, there's a couple of different kinds of equilibria that you have to consider when you're doing these equilibrium problems. If you have to calculate the pH of the solution, you have to consider, are you dealing with a strong acid or a strong base, or a weak acid or a weak base? And those require different approaches. Sometimes we have to consider water reacting with itself. And that's its own kind of equilibrium problem. Okay, one thing we're going to do today, and that this recorded lecture snips talk about, all of the pH calculations and all the equilibrium constant values we have apply to a single kind of reaction. A reaction with water. What if an acid reacts with a base that isn't water? Do the Ka values, can we use those in a rice table? No, we can't. So we have to have a way to predict equilibrium under those conditions, and we'll talk about it in a minute. Okay, so if we're setting up a rice table and we're filling out our initial line in the rice table, or an acid base in reaction with water, you have to put hydronium in the initial line in the rice table, right? What is it?
Product.
The product. What is the actual concentration before you start? You're in a neutral solution, like just regular water. What will the hydronium concentration be before you start? 1 times 10 to the minus 7th molar. It will be, okay? Because when you do the equilibrium calculation based on the Kw and solve for the equilibrium calculation of hydroxide and hydronium in this reaction, you get 1 times 10 to the minus 7th. So what we assume is that that's the concentration of hydronium that we have all the time in water, as long as we haven't added anything extra to it to shift that equilibrium. Okay. How do we solve this equilibrium problem? First thing, you need to know what kind of acid you're dealing with. HCl, is it a strong acid or a weak acid? Okay, it is a strong acid. You don't have to know that because why? What reference material can you use to always answer that question for you? Pull up the Ka table, look at HCl on your Ka table. You'll see it's positioned as a strong acid. It has a high Ka value. It's a strong acid. How do we write the rice table? So there's our reaction. HCl reacts with water. Or we could have written it according to the Arrhenius. The product, when it dissociates, you can write it as H plus or hydronium and the chloride ion. Before the HCl reacts, I don't have any chloride in solution, right? Assuming that there's not sodium chloride or something in there. Why do I write approximately 0? Is it actually 0? Actually 1 times 10 to the minus 7th molar. We care about 1 times 10 to the minus 7th molar if we're adding 500 millimolar acid. No, it's gonna swamp out whatever was there with the acid, with the hydronium before we started, so we're not really worried about it. Okay. Are you allowed, if it's a strong acid, to simply assume that all of the starting material becomes product? Yeah, you are. Strictly speaking, is that 100% accurate? No. Are you allowed anyway? Yes. Okay. So the HCl is going to be completely product. So all of our starting acid becomes 0.5 molar H plus or 0.5 molar 0.5 molar chloride. Okay. So you just take minus log of that 0.5 molar hydronium concentration. That gives you that we would expect. About pH values. A neutral solution is pH 7, right? What range do we see in acidic solution? So an acidic solution has more hydronium in it than 1 times 10 to the minus 7th. So what happens to the pH values? It's lower than 7. Okay. If we added 500 millimolar concentrated hydrochloric acid, that's going to be a pretty dang acidic solution, right? I don't want that touching my skin. That pH value approximately where it should be. Yeah, it's quite a bit lower than 7. So we know it's quite acidic. And POH, you just take 14 minus pH 13.7. Okay. Is that where you would expect the POH to be? If you have a solution that has a lot of hydronium in it, what does that say about how much hydroxide is in that solution? The product of the hydronium and hydroxide solution has to equal the kW of water, right? So if hydronium is high, what do we know about hydroxide? It's low. Okay, so we go back to this HCl solution. We added a whole bunch of hydronium. pH is low, meaning we have a lot of hydronium, which means we have to have not very much hydroxide. So the POH should be high, meaning there's not very much hydroxide. That's what it is. All right. What if we have a different acid? This is formic acid. You look up the Ka value on the table. The Ka is 6.3 times 10 to the minus 5. This is a reasonably strong weak acid, but still it's a weak acid. Set up a rice table. I could have done it with hydronium. It says it's expressed in the Arrhenius model. Exactly what you have learned how to do before. Okay, so we set up our Ka. It's the products divided by the starting acid. Why doesn't water show up? I mean, we haven't written it in the Arrhenius model, but if we wrote it in the Bronsted-Lowry model, water would show up in the equation. Why doesn't it show up in our Ka value?
Liquid.
It's a liquid, it just falls out. Okay, x squared divided by 0.100 minus x gives us our Ka value. Tell your neighbor from unit 2 how you would solve that. The foolproof way is you can always use the quadratic formula and it will work, right? Great. Some laughter. In theory, the quadratic formula will always work. In my hands, does the quadratic formula always work the first time?
22%.
Doesn't always work perfectly for me because I'm sure to make a mistake somewhere. Okay. So what we hope to do is make a simplifying assumption so we don't have to use the quadratic formula. If x is very small, then 0.100 minus x might actually round when we report our final concentrations to 0.100, and then we can just pretend the x isn't there. Okay. So if we do that, we substitute 0.100 in instead of 0.100 minus x and solve for x, and we get this value. How do we tell if the assumption was a good one? How do we test that we did it right?
Yeah.
Take that x value, plug it back in to your formula and see, do you get 6.3 times 10 to the minus 5? Okay, Notice a complication here. When I do that, do I exactly get the right K value? Don't. My K value is off. Well, what does that tell me? Let me say it louder.
In water.
Well, you're actually supposed to forget water. So that's not a problem. What it tells us is that 0.100 minus x isn't actually close enough to 0.100 that that was a very good assumption. So what do we have to do now?
Go back and do the quadratic.
So the foolproof way, assuming that the math is foolproof in your hands, is to plug it back into the quadratic formula and just solve with the quadratic formula. If you have a calculator that solves the quadratic formula for you, and you can plug the numbers in the right place in the calculator, always a problem for me personally, then that works just fine. There is actually a new way that I'm introducing to you, sometimes called the iterative approach. The value of x that we calculated, is it way wrong or just a little bit wrong? It's just a little bit wrong. Is the value for x closer to the real value for x than assuming that x is 0 is? It is. So the x that we calculated, it's not exactly right. But we could, instead of assuming that 0.100 minus x is equal to 0.100, what if we took our close but not quite right value for x, plugged it in the denominator? Can we do that? We can. And that is the iterative approach. When we do that, will we resolve for x and get a number that in theory is closer to the real value? Yeah. How will we check if it's close enough? Plug it back in and see if we get K again. Okay, so this is what we're gonna do. We calculated a value for x. We checked our value for x by plugging into the K expression. The answer was not quite right. Okay, so instead of going back and doing the quadratic formula, which is what you would have had to do in unit 2, you can take this 0.100 minus x and just there, just where you're subtracting it, take the value of x that was close but not quite right and use it there. So we start with our, set it up the way you normally would. And then instead of subtracting x here, subtract your close but not quite value of x that you already calculated. So these didn't go in the right way. So when you do 0.100 minus x, substitute in your value that was close but not quite. Then resolve for the x in the numerator. Now it's pretty easy. And when you solve for that, you get what 4 times 10 to the minus 30. You can plug that into your K expression.
Yeah.
Yeah. That's way easier than the quadratic formula. Okay, sometimes if you do that once, you still won't get the right K value. What can you do then?
Quadratic.
You can do the quadratic formula, or you can try plugging it in one more time. Eventually you get there.
What about sig figs? Because one thing that kind of annoys me about sig figs is if you follow them to your answers and then plug in your sig fig controlled answers for X, then you might not get the same PKA.
So don't round for sig figs at any point until you report your final answer. Carry all your digits until you're reporting your final answer. That's the only place that it matters. There is one complication, and that is, did we teach you significant figures for taking the minus log of things? No, we didn't. So you can calculate your final concentrations and know how many sig figs you're supposed to have there. What do you do when you report the pH? I give you permission to just report with 2 digits all the time, because that's typically what people report, because that's what a pH meter measures. So the whole significant figure thing kind of falls off the map in Chem 105, 106 terms when we get to pH. Okay. So normally, aside from throwing at you this iterative approach, which some of you will reject completely and not ever use, and some of you will love and use all the time, pretty much the same thing you've done before, right? Except we assume that the starting concentration of hydronium is 0. Why do we do that? It's not really true, is it? Why do we do it? Mostly true. Will a chemist settle for nearly true or mostly true? It doesn't affect the final outcome. Good enough, right? There is one example where it does affect the final outcome. Excellent here. The reason we can say that this is 0 here is because we're adding a whole bucket load of acid, right? So the hydronium that the acid is adding is going to be so much bigger than the hydronium that the water is adding that we're not even going to care about the hydronium that comes from water. However, what if we only add the teeniest bit of acid to our water? Now are we swamping out how much hydronium the water is contributing? Not anymore. Okay, we have a 30 nanomolar solution of HCl. What is the concentration of hydronium that the HCl is adding to the water? So let me draw out sequentially what's happening. Change my. So if I have HCl and I add 30 nanomolar HCl, that's going to react with water and we're going to form hydronium and chloride ion, right? 30 nanomolar. Remember what the prefix nano means? 10 to the minus 9. This is 30 to the minus 9 molar, or 0.3 times 10 to the minus 7 molar. Okay, put that in context with so if we're doing this rice table, what kind of acid is water or is HCl? It's strong, right? So when it reacts with water, it's going to react. When it does, we know exactly how much hydronium is added to our solution that comes from the HCl, right? Big amount or small amount? Okay, how much is the water contributing? So we have two acid-base equilibria going on, right? One is the HCl reacting with water. One is water reacting with itself. The HCl adds 0.3 times 10 to the minus 7th molar. Water adds 1 times 10 to the minus 3 molar. Okay, can we ignore what water is doing here? No, now we can't. Okay, let me. Here's the problem. So we can't ignore what water is doing. Before we added the acid, we know what this concentration is for hydronium that water is adding, right? How much is it? 1 times 10 to the minus 7th molar. But we just added a little bit of acid. So what happens to this equilibrium? It shifts. So do we know how much total hydronium we have? We don't even know how much we have. We know how much we have from the HCl. And what do we know about how much we have from hydronium? Less than 1 times 10 to the minus 7. Because as soon as you add hydronium, this is going to shift towards the left. So we don't even know. How do we find out? So what you have to do is you have to say, I actually have to do a common ion effect equilibrium calculation to figure out how much water reacts with itself in the presence of some added hydronium that comes from the HCl. So how we do that is we say, okay, let's assume that the water hasn't reacted with itself at all yet. Can we use the equilibrium constant for water reacting with itself to calculate how much it would react in the presence of added acid? Yeah, so we write our initial line. We're not gonna have to worry about those. The hydronium that we start with is the hydronium that comes from the HCl addition. Okay, so we're assuming, start with this water autoionization unreacted. And do a rice table calculation and say, where does the equilibrium lie in the presence of the added acid? So what's my change line gonna be? We're gonna get some amount of hydronium from the water reacting with itself, and some amount of hydroxide. So what does my equilibrium line look like? Our equilibrium line looks like that. All right. And then we just do a rice table calculation. Is there any set of simplifying assumptions we make here? Can we neglect X anywhere? Can we use the iterative approach anywhere? We can't. So this is just an ugly quadratic formula. Okay. When we solve for X, what does X tell you? What does the X value mean in this context? Here, let me put this back on the right. What does the X value tell you? X tells you the concentration of hydronium that comes from the water autoionization. Okay, when I calculate my pH, can I use that value? When I calculate my pH, I have to use pH of X plus 3 times 10 to the minus 8, which gives you a different pH value than just based on X. So go through and think that through. If you need to see these again, the Gilbert textbook is a pretty good example of how to run this. Allie.
Did we ever do an example where it's not a strong acid that dissociates?
Oh, good question. Would I ever give you a problem where you had a very dilute quantity of weak acid added to water? And you'd have two different equilibria both lying on the left that each influence each other.
That's scary.
What would a chemist do in that circumstance? Pull out the pH meter and measure it. That's what they would do. So I won't ever give you one like that. That would be cruel and unusual punishment, and I'm not even sure how I would do it. Okay, what if you did a pH problem of a strong base? Okay. Your Ka table doesn't have a lot of strong bases. If I give you a base and it doesn't show up on your Ka table and it doesn't show up on your pKa table, is it fair to assume that it's a strong base? Maybe. The strong bases that you are going to see, you'll see NH2 minus. Anything with a negative charge on a nitrogen is going to be a strong base. Anything with a pKb value greater than 10 to the minus 14 will be a strong base. Anything with conjugate acid has a Ka that's less than 10 to the minus 14, that base will be a strong base. Okay, so they tell you they're reacting sodium amide. That's the formula for sodium amide. Do we actually care about the Na plus? We don't. So the real reaction is amidion reacts with water to form ammonia and hydroxide. Okay, so the rice table, if amide is a strong base, then all we have to do is say all of our starting material gets converted to product, just like in a stoichiometry calculation. So whatever number of concentration or number of moles we have in our starting material is all going to become product. Can I do a pH calculation directly from that rice table? What we calculated is the hydroxide concentration. What do you have to do to get pH from the hydroxide concentration? You can convert it to hydronium concentration via the KW and then take pH. Or you can take that 0.5 molar, convert it to the POH minus log of 0.5, and then get the pH from that. Do I care which approach you use? No, I don't. Okay, so then the pH, 13.7. Why should the 13.7 pH feel like the right number to you? Okay, if you add a strong base to water, you should get a solution that's strongly basic. 13.7 in aqueous solution, 14 is about the most high pH you can get. So 13.7 is pretty close to maximum pH, maximum basicity. That's what someone had a question in the back. No. It's a weak base problem, then finally you can take a break, right? What if instead of sodium amide, we did ammonia, which doesn't even have a negative charge on the nitrogen? Then we find ammonia on our pKa table or a Ka table. It's the conjugate base of ammonium ion. It is a weak base. Okay, so if I said I have a 0.3 molar solution of ammonia, tell me the pH. What are we doing here? We're taking our weak base, we're adding it to water. It's reacting with water. Where does equilibrium lie? To the left. Okay, so we set up our rice table. X times X divided by 0.3 minus X equals the KB value. Why can't I just use the Ka value here? How is this reaction not the same reaction that you'd apply a Ka value to? What's the product in the Ka expression? It's hydronium. What are we creating here instead? Hydroxide, so we have to use the Kb. Okay. If you don't have the Kb, what do? Say ammonia is the conjugate base of ammonium, so I'll look at the Ka table and I'll find out what the Ka is for ammonium and just calculate the Kb. Do that. Standard rice table calculation. You can neglect X in the denominator here. And that gives us 2.3 millimolar hydroxide concentration. From there, you can calculate your pH. You just have to go through a bunch of different steps to finally end up with pH. Okay. Take a break. Your recitations from downstairs. Walk around. Watching somebody else do math on the whiteboard or on the is about as painful as it gets. The only thing works is not this. I am super. That might just not worth doing. Like asks a question.
I was like, if you mix this whole time. What I thought the net. That's too low. This is given to us, so. This. It's gonna react to this. That's the ion wall. But for me, I think we did that one. We never did centrifuge. So this one, usually you with them. She has a video on this problem. This is these two right here. These two, or that one, and then the final. I'm pretty much just based off the video. She has a video where she wants to approve 3 different points. Yeah, this part. I interchange it. Spectators. You just got it wrong. Well, she didn't know exactly, but I got the idea. It's like how you- Goes back and forth.
You can comfort yourself that at least you're not a 105. You're doing heat transfer problems today.
Seems like I don't at all. I'm so
What about for
weak
you
at it.
guys? Do one of those.
Sure.
Did you get me one too?
Yeah, sure.
Yeah, dude.
Too nice to us. Thank you so much. Seems so cool.
The recitation is.
All right. One calculation, you should just have ionization. Percent ionization is just another tweak to a rice table calculation. So if you look at the formula, the percent ionization equals the hydronium in that solution at equilibrium. Calculate the hydronium ion concentration in solution using a rice table. Then we divide by something else. Where does this initial concentration of your acid show up on the rice table? Yeah, it's the top right hand. So here's a supposed to be an example. Let's switch slides here. So formic acid. We're in the formic acid solution. We did a previous equilibrium problem. The question could have said, instead of calculating the solution pH, it could have said, calculate the percent ionization. Instead of your rice table, you solve for X like you would normally have done. Iteratively. I guess this is a different concentration. All the ways that you would normally solve for your value of X. Okay. When you finally get an X value, it gives you the right Ka value back again. That is your so the percent dissociation is your X value that you solve for here. That's your hydronium concentration. Then you divide by the 0.200 value that you put in the top corner of your rice table. Yes.
Do you have to square your X value? A is there too?
So this is your Ka value. So that's just the Ka value. And you use the Ka value to solve for X, right?
Yeah.
Once you have X here, that X, if we go back to our formula, that X is your hydronium concentration equilibrium.
Right, okay.
So then you take the X, divide by your initial concentration, multiply it by 100 to get the percentage. That's all you have to do. So it sounds like a different kind of problem. It's just the same kind of problem. We're going to skip this because we're going to run out of time. Okay. Up to now, all the discussions we've had pretty much have been what happens when you react the acid with water or you react the base with water, right? A very small subset of the possible acid-base reactions in the world. Because you could have a Bronsted-Lowry acid-base reaction of any acid reacting with any base. How do we know where the equilibrium will react to those? We don't actually have an equilibrium. You have to extrapolate. And actually, you're going to be really good at extrapolating. It makes a lot of sense. Okay. We can use the strength of the acid and the base and the strength of the conjugate acid and the conjugate base to figure out which way the equilibrium will lie. You can get information about how strong the acid and base are and how strong the conjugate acid and the conjugate base are from the Ka. Theoretically, this is our standard way of thinking about a Bronsted-Lowry acid-base reaction. Okay. If your base, starting material side, is stronger than the conjugate base, what happens to that reaction? Okay, Ali says when the base is stronger than the conjugate base, equilibrium will lie on the side of product. Somebody explain why that's the right answer. Can we see it as a competition for the proton? When the reaction is moving forward, the base is taking the proton, right? When the reaction is moving backwards, the conjugate base is stealing the proton back, right? So if we can say which one is better at keeping the base, do we know where the equilibrium will lie? So if the base is stronger than the conjugate base, which one is better at keeping the proton? The base. So which way is the equilibrium going to lie? On the side of the reaction where the base has the proton product. Okay. So if the base is stronger than the conjugate base, equilibrium lies to the right on the side of product. If we had an equilibrium constant for that reaction under those conditions, what would it be? Greater than 1. Okay, when the conjugate base is stronger than the base, which reaction will work better? Backwards reaction will work better, so where will equilibrium lie? On the side of the starting materials. So to the left. Yeah. Is that as hard as it is? Yeah, that's as hard as it is. Okay, so all you have to do when you have a reaction where water is not the acid or the base, you don't have an equilibrium constant. All you have to do is write out the reaction and then say, is the base stronger or is the conjugate base stronger? That will tell you. How do you decide if the base or the conjugate base is stronger? So we could analyze it by looking at stabilities, right? Is there an easier way? You can just look at the position on the Ka table or look at the Ka or the pK. In perspective, this analysis where we only have to decide where the equilibrium will lie. If you have a strong acid reacting with a strong base. Let me write it out for you. This is relevant because it applies to titration. Well. Okay, with our acid, we're going to make it a charged base. Our acid reacts with our base. We're going to form the conjugate acid, or the conjugate base plus the conjugate acid. Okay. If this acid is strong, what does that tell us? What does it tell us about the conjugate base? It's weak. How weak is it? It's so weak, it's unreactive. Okay, so where does equilibrium lie? It has to lie all the way to the right. If a strong acid is reacting with any base, are most bases stronger than water? Actually, yeah, water's it's not a very good base. Good enough that it can react with acids, but not great. Okay, if you start with a strong acid, equilibrium is going to lie all the way to the right. Okay, what if? Well, that was a strong acid with a strong base, right? So if this is strong and this is strong, what does that mean about both of these? They're both weak. So where does it have to lie? All the way to the right, right? Because the forward reaction is going to be way more effective than the back reaction. Okay, let's do a strong acid reacting with a weak base. This is what we just did. What is the strength of the conjugate base of a strong acid? That's where it shows up as unreactive. What's the strength of the conjugate acid of a weak base? Also weak. Now, the weaker the base, the stronger the conjugate acid, right? But it's still going to be classified as a weak acid. It can be a stronger weak acid or a weaker weak acid, but it's still a weak acid. Okay, where does equilibrium lie? All the way to the right. As long as one of the things on the starting material side is strong, that's enough to push equilibrium all the way to the right. Okay. What if this is strong, this is weak? Now what?
Still gonna lie to the right.
Okay. The conjugate base of a weak acid is going to be, it's still going to be weak, but it will have some reactivity, right? How about the conjugate acid of a strong base? How weak is it? It's unreactive in water. Okay, where does equilibrium lie? All the way to the right, because that the conjugate acid of that strong base is not going to react back. So equilibrium lies all the way to the right. Okay. But this is a situation where we have to extrapolate and figure it out. A weak acid reacts with a weak base. You get weak and weak. So the question is, what's weaker? Starting material side or the product side? That's what we have to assess using the Ka.
Can you please explain why all four of them are weak?
It's complicated. Okay, so the question was, can we explain why all of them are all the in that diagram, why they're all weak? Why is the conjugate base of a weak acid a weak base? And why is the conjugate acid of a weak acid a weak base? If I actually said all those words right, that's pretty. So chemists use the term strong and weak in really dumb ways. Okay, probably the textbook or somewhere that you read said the conjugate base of a strong acid is weak. Did you hear that? Okay. But you've also heard that the conjugate base of a weak acid is a weak base. You heard that too? I've heard both of those things. The problem is that the word weak is not used in a very finessed way. So sometimes weak means everything that isn't a strong isn't strong. Okay, so the conjugate base of a weak, the conjugate acid. I shouldn't have made a comment about saying words the right way because now they won't come out of my mouth the right way. Start with a weak acid. Tell me about its conjugate base. It's reactive, but not hugely reactive. So we call it a weak base. We say the conjugate base of a weak acid is a weak base. But it's weak, but still can react with water. Compared to the conjugate base of a strong acid, chemists still call weak. But is it the same kind of weak? It's unreactive weak. So I think that's the source of the confusion, right?
Is that because like because of the whole KW, KA thing, like if it's a really low KA, then the KB is still gonna be low. To get to -14.
Partly. And partly it's because the same things that stabilize a conjugate base make the proton held on less tight.
So the conjugate base of a strong acid still isn't enough to make the equilibrium line to the right.
Yes. So Josh says the conjugate base of a strong acid doesn't have enough reactivity to cause a back reaction, essentially. Right? Is that fair?
Yeah.
Yeah. Okay. So as long
I have a
as one of your starting materials in an acid-base reaction is strong, where will equilibrium lie?
Right.
All the way to the right. If they're both weak, you have a weak acid reacting with a weak base, then you have to figure out what's going to happen. So let's do some examples about how you would do that. Let's see. Okay. Rationale. We're seeing this reaction as a competition for the proton, right? So we have to say, whatever side of the reaction is more reactive, equilibrium will lie on the other side, right? Which we can assess by saying, essentially, is the base stronger? Or is the conjugate base stronger? And whichever base is stronger, whether it's on the starting material side and the product side, what will that do to the reaction? The stronger base will grab the proton and keep it, which does what to the equilibrium? Pushes it to the other side. Okay. So when the base is stronger than the conjugate base, which way will the equilibrium lie? The stronger base then grabs the proton and keeps it, so the base wants to exist in protonated form, so equilibrium lies on the side of product. If, however, the conjugate base is stronger, what's that going to do? And the conjugate base is going to win the tug of war for the proton, and you'll end up with more product.
So do bases in their like on the left side form when they're not conjugate, do they usually have just like a rando ion to like, okay.
Okay, so Josh says bases, like if you're doing a reaction and the base is a starting material, will it have a counter ion associated with it? So like this, we draw it as a B minus, right? A base with a negative charge. And it could be any number of weak bases. Carboxylate, hydrogen sulfate, fluoride, it could be any number of things, right? When we actually build this reaction, we're mixing it up on the bench top. This negative ion comes with a positive counter ion. Sodium or potassium. Okay. So when the base is stronger than the conjugate base in a Bronsted-Lowry acid-base reaction, that pushes equilibrium to the side of products. How can we easily assess on a Ka table, or in this case, a pK table, which one is stronger? Where will we find the stronger base? Stronger base has the more positive pK value or the higher Ka value, which means it will be found where on the table? Lower. So if the conjugate base, if the base is below the conjugate base on the table, that means it's a stronger base. This means it will push equilibrium to the right. Some examples. Okay, if we have trifluoroacetic acid reacting with fluoride ion, which would be like sodium fluoride if we were using the whole formula. Okay, so think about this. Trifluoroacetic acid, that's your acid, reacting with fluoride, that's your base. Will you off the top of your head know what the structure of the conjugate base of trifluoroacetic acid is? Look it up on the table. Where is it? The first one. We can draw it. Or you can in your head think trifluoroacetic acid has a conjugate base trifluoroacetate. So this is. Will I give you things and expect you to just know what's formulas are. I could, how effective would that be? Not so effective, right? Effective for some of you. Can you figure out the formulas from the tables? Or you can. Okay. So there's my reaction. Sess. What do I know about the acid and base strength? Okay, someone said fluoride is stronger. How do we reason that through from the table? If I'm comparing CF3COOH to hydrogen fluoride from the table, which one is stronger? So where are they on the table? Is HF on that table? Somewhere. Halfway down. Okay. So trifluoroacetic acid is higher on the table and has a more positive or smaller positive pKa value versus HF. What's a stronger acid? Trifluoroacetic acid or HF? Okay, that's our stronger acid. My weaker acid when I'm comparing. Okay, my stronger acid, what does that mean about the conjugate base strength? The stronger the acid, the weaker the conjugate base. So that makes this the weaker conjugate base. And this the stronger conjugate base. Which way will the equilibrium lie? The side of product. When you do this analysis, will you always get stronger and stronger on one side and weaker on the other side? Yes, you will. The relationship between the strength of the conjugate base and the strength of the acid means you will, when you do this analysis, you always get the stronger acid and the stronger base on one side of the equilibrium or the other. Okay, what if instead of trifluoroacetic acid, we did citric acid? Okay, citric acid, when it donates a proton, becomes citrate ion. You can figure out the formula structures if you want, but you don't really have to. Plus HF. Okay, where's citric acid on the table? So citric acid has a pKa of 3.13, right? Hydrofluoric acid, what pH is it? It has pKa. Okay. Now we can say when the base is lower on the table than the conjugate base, then equilibrium lies to the right. So our base here is fluoride. Our conjugate base is citrate up here. Our base is stronger than our conjugate base. Which way does equilibrium lie? To the side of product. Or we can simply look at the pKa values and figure out. Okay, if citric acid has a pKa of 3.1, HF has a pKa of 3.2, which one is stronger? Okay, the lower the pKa value, the stronger the acid. So this is a stronger acid, which makes this my weaker acid. Conjugate acid. Okay, the stronger acid has what kind of conjugate base? Weaker conjugate base. The weaker the acid, the stronger the conjugate base.
Yes.
Equilibrium lies on the side of product. Yeah. Okay. I could ask you where the equilibrium lies, or I could use chem speak, talk like an organic chemist and say, will aspirin be deprotonated by sulfate ion? Okay, what's aspirin? You guys obviously didn't. Here is the history of me becoming a chemistry geek. I also really like words and language. So I remember as a 9 or 10-year-old sounding out the label on an aspirin bottle. acetyl salicylic acid. Okay, so aspirin is acetyl salicylic acid here. Okay. Will aspirin be deprotonated by sulfate ion? What are they really asking? If you react acetyl salicylic acid with sulfate ion, which is here, will equilibrium lie on the side of product? So if base is stronger than the conjugate base, equilibrium will lie on the side of product, right? What's stronger, the sulfate, which is the base, or the acetyl salicylate, which is the conjugate base? No, the conjugate base is stronger. So which way will the equilibrium lie? On the side of starting materials. It's out in a minute. So what does that say about whether aspirin can be deprotonated by sulfate ion? A lot of connections, right? Once you learn how to make them, it's not actually that hard. Okay. We'll call that acetyl salicylic acid. What's the pKa value? Okay, plus sulfate ion. So we get salicylate ion plus protonated form of sulfate, which is hydrogen sulfate. Okay, what's the pKa of HSO4 ion? Probably put on here.
1.12.
Okay. What's the stronger acid? This has a lower pKa, so this is a stronger acid. And this is weaker. Where's equilibrium going to lie? On the left. Okay, you can go through that and say, okay, the stronger acid can have the weaker base, and the weaker acid is going to have the stronger base. And spell it all out. Which way does your equilibrium lie? On the side of starting materials. You could also just say, from the position of the base and the conjugate base in the table, I can tell you that the product base, the conjugate base, acetyl salicylate ion, is going to be a stronger base than the reactant base, which is sulfate. The equilibrium will lie on the left.
So that equation that would happen when you put
Aspirin with sulfate ion. So that's answering this question.
and then but it'd also be aspirin with the hydrogen sulfate ion, right? So like two acids together also make an acid base equal.
No, we're reacting with sulfate.
With just-
Base is just sulfate.
But there is a case where like if you put two acids in a solution, there's two
We
acid.
could have used hydrogen sulfate instead, and then it would be a little messier and it would be different analysis.
Will we ever have to do that? Like two acids together and then there's two acid base equal of the conjugate base and then the acid and then the conjugate acid. Wait, see?
Probably not. Okay. If we take aspirin, instead of reacting it with the sulfate ion, we react it with oxalate. Where?
19.
Okay, yeah. Here. What will happen then? The oxalate is strong enough base to pull a proton off of salicylic acid. The conjugate base is this. Sorry, I have that wrong. This is your base, this is your conjugate base. Which one is stronger?
Base.
The base, which way will the equilibrium lie?
Right.
To the right. Okay, go through that logic. There are videos. I think there's a Professor Dave video that talks about how to do this. There's a video of me talking it through on the PowerPoint video. Not gripping, it's just me talking about the PowerPoint slides with a little talking head in the corner. Okay. When you have a chance, listen to Acapella Science talking about vibrations. What song do you think this is going to be a cover of?
All about that bass.
Yes, the lyrics go, it's all about the bass, no acid. So sometime when you need to listen to something silly, that's helpful. Okay, let's talk titrations. Half an hour, 15 minutes for titrations and 15 minutes for polyprotic acids. Do you remember doing the stoichiometry calculations in Chem 105?
Yes.
When you did a stoichiometry calculation, you figured out how many moles of starting material you had. And then you said, if all of those moles of starting material get converted to product, how many moles of product will I have, right? Titration reactions are just a different form of the very same process. So let's talk about it for a minute. When we do a titration, what we are doing is setting up an acid-base reaction under conditions where equilibrium will lie completely to the right. So, a common way, you guys do the CHP plus hydroxide titration in Chem 107, pink indicator. Did you do an acid-base titration in Chem 107? Okay, and you reacted a weak acid, I expect, with sodium hydroxide in your urette, right? Okay. What acid did you use for your sample?
Acetic for the week.
You used acetic acid?
Yeah.
So you all went home smelling like vinegar?
Yeah.
Okay, weak acid. Okay, in a titration, we're just doing an acid-base reaction and setting it up so we get 100% yield like in a stoichiometry calculation. Okay, what kind of acid or base do you have to use to get 100% yield? Something has to be strong with your starting materials, right? Either your acid or your base have to be strong. And when we set up a titration reaction, we make sure that whatever we put in the burette is strong. And then, because one of the things is strong, what happens to that reaction? It reacts completely, which turns it into essentially a theoretical yield kind of problem. So all of our principles are, do we use the K value and what do we do for the equilibrium? Do those apply to titrations? They don't. In a titration, we assume that all of the starting material that can react reacts to form product. And it's just a mole ratio problem like you did in Chem 105. Okay, why do we do titration? The whole principle of titration is lots of times we need to measure how much stuff we have in a solution. We use titrations to do that. So if we have an acid solution that's of unknown concentration, we need a way to test how much we have, right? So we do a titration reaction where we put the unknown sample in our little flask here, and we react it with a strong base. Strong base. Drive the reaction all the way to the right. So we would react it with strong base. And we add just enough base to react completely. Or we have a way of tracking when the reaction is done. Okay, if I have a certain amount of acid, when will that acid be done reacting? Careful, you always want to say equilibrium, but equilibrium is achieved immediately as soon as we add stuff. If I have 1 mole of acid, how many moles of hydroxide do I have to add to react all of my starting material? 1. And that's what a titration does. You add enough hydroxide to react all of your acid, and then you know how much acid you've had. Okay. What if instead of an acidic solution, you have a basic solution? You want to know how much base is there. We do the same thing, except if this is a base, what do we put in our burette? An acid. Okay, what kind of acid do we want to use? Strong. Now, typically, we use hydrochloric acid because every lab has it and it's cheap. And when we're reacting in the opposite direction here, when we want to use sodium base, we use sodium hydroxide because it's cheap and every lab has it. And it exists as a solid, so it's easy to weigh out. That's pretty much always what happens. Okay, so if we need to know how much base is present in an unsolution, then you react it with hydrochloric acid. Okay. There's language that people use to talk about this. They talk about neutralizing the solution. What does neutralizing the solution mean in this context? It means that you add just enough hydroxide to react with all of your starting acid, or vice versa, so you don't have any left over. That means you add enough of your hydroxide, just react with your starting material. Maybe this will start to make more sense when we do it. Okay, how do you know if the goal is to only add enough of the stuff in your titrant to react with what you have in your sample? How do you know when you've reached the end? If I've added just enough hydroxide, for example, not any extra, and I've added enough hydroxide to just use up all of my starting material. When I'm left, I've taken all of my starting material and converted it to the conjugate base, right? And all of the hydroxide has become water, right? So can I tell from the pH whether I'm done or not? If I add too much hydroxide, what's going to happen to the pH? We'll have the pH being affected by added hydroxide, so the hydroxide will go up, right? So what we can do is, if we know what pH we're going to have when we're done reacting all that we started with, we can put a pH meter in it, know when we're done. A more old-fashioned approach is to say there are dyes that change color at given pHs. So you add a drop of that dye into your solution, and when you get to the right pH, your solution changes color and you're done. In Chem 107, you used a pink indicator, right? A pink dye. Phenolphthalein, was it?
It was blue.
Was it blue? Okay, a different one, not phenolphthalein, but yeah, that just tells you. Okay, language here. In the titration, what we call the sample typically is a solution that we don't know what the concentration is. And usually that's what you're dropping your titrant into. Sometimes the sample is called the analyte. You can recognize the sample in a problem because you don't know how many moles of it you have. So often they'll tell you the volume, but not the concentration. Because concentration is what you're trying to do. I'm trying to figure out. They could tell you concentration, but not volume. That works too. Okay, the titrant is the solution that you're going to drop in to make the reactions. Typically what's in the burette. In a problem, how do you recognize the titrant?
What's maybe, yeah.
It tells you the volume that you added and the concentration. And then you know. Okay. They also talk about the end point or the equivalence point, and that's the point at which you have added enough of your titrant to completely react with your starting sample with none left over. So the end point, this is in Chem 105 terms, in a stoichiometry problem. We have problems that say, how many moles of starting material do you need to react completely with some amount of another starting material, right? Okay, the end point is when you have a 1-to-1 mole ratio of your acid and your titrant, if you have a monoprotic acid. Okay. Someone asked me in the reading quiz, where does the equilibrium lie for a reaction that occurs in a titration? Where does equilibrium lie? All the way to the right. So do we actually talk about equilibrium with respect to titrations? No, we don't, because we're assuming that all the reactions occur completely because we're using a strong acid or a strong base as our titrant.
I was thinking completely that will be like, even for a weak acid being titrated strong.
Yes.
It will all just go to the right.
Yes.
Okay.
Okay. Typical titration problem. You have 25 milliliters of acetic acid. Is that your sample, your analyte, or your titrant? Which is it? That's your sample. It says sample, right? So that's what you don't know. And you're going to titrate it with a strong base, which is sodium hydroxide. And they tell you that when they did the titration, it took 12.15 milliliters of a certain concentration of sodium hydroxide. And they ask you, what was the concentration of the solution that you started with? Okay, so the first thing to say is What's the reaction that's gonna happen? In a titration, the reaction is always your sample plus your titrant. For a sample of acetic acid, our titrant is hydroxide. They say sodium hydroxide. Do we care about the sodium ion? We don't. Okay. Hydroxide is a strong base, so it's going to totally take the proton off of the acetic acid, form the conjugate base in water. Sample of acetic acid, and what are we titrating with? Sodium hydroxide. Okay. Can we calculate exactly how many moles of sodium hydroxide we used? If you take the concentration in moles per liter and multiply it by the volume in liter, what do you get? You get moles. So we have enough information to calculate exactly how many moles of sodium hydroxide we used. If we know the number of moles of sodium hydroxide we used, do we know the number of moles of acid that we reacted it with? Is that the same as the total number of moles in the acid sample? Yes, it is. So this is just a stoichiometry problem. You calculate the moles of sodium hydroxide by multiplying the concentration times the volume of sodium hydroxide. So the 1-to-1 mole ratio of hydroxide and acetic acid. And then you calculate your moles of acetic acid. So we calculate our number of moles of sample. We're essentially doing a stoichiometry problem here. We take a concentration times the volume of sodium hydroxide. What's going to cancel here? Our liters cancel, we're left with moles of sodium hydroxide. What's the mole ratio of sodium hydroxide to our acetic acid? 1. Okay. So that gives us this would be 0.02356 moles of acetic acid, right? How do we calculate the volume? How do we calculate the concentration if we've given the number of moles? Divide by the liters. That's all you have to do. Could I have done it in one step? Yeah. It's really just a stoichiometry unit conversion problem. That's all it is. Could also track titration with a titration curve. And the titration curve, what you do is you just put a pH meter in, and then you record as you drop sodium hydroxide. And the advantage of doing this, for those of you that cursed titrations in 107, wouldn't it be nice if you could set it up and walk away? If you do a titration curve, you can automate that you're adding stuff to your sample and just come back later and analyze your titration curve. Okay, if we are titrating a strong acid, which is hydrochloric acid, right? We're titrating it with sodium hydroxide. What we're getting is HCl reacting with hydroxide to form chloride ion plus water. Okay. At the end point of the titration, what we've done is taken all of our HCl and converted it to chloride plus water. We haven't added any extra sodium hydroxide. So the only thing we have present in the solution is chloride ion and water. If I have a solution of chloride ion in water, what should the pH be? Should be 7. Salt doesn't increase the pH of a solution. So if we're titrating a strong acid, the pH of the endpoint is 7, and that's what it shows here. So from the appearance of the curve, how do we recognize the equivalence point for when the reaction is done? It's the midpoint of the steep section. That represents the volume of sodium hydroxide at which we've added enough moles of hydroxide to react with all of the starting acid. So that point there represents the volume where we have 100% conversion of our starting material acid to the conjugate base. So we start here, and in the sample we have all HA. At the midpoint, or at the end point, we have only A- left. Okay. Examine these plots and tell me what kind of material is the titrant and which one is the sample. But what are we measuring the pH of? A sample, right? So this one, pH starts below pH 2. What kind of material is our sample? An acid. Okay. And so then we must be titrating with what? A base. Equivalent point is at pH 7. What does that tell us? We're titrating a strong acid because when we completely converted the strong acid to the conjugate base, it's unreacted with water and the pH is going to be 7. Okay, this one, what's our sample? The base. How do we know? We start at high pH. And then as we titrate to the equivalent point, we must be titrating with an acid, probably hydrochloric. Okay. We're going to skip that one, come back to it. Okay. So if we're titrating, if our sample is a strong acid or a strong base, what's the pH of what we get at the endpoint? What's the solution pH at the endpoint? pH 7. Exactly. Okay, what about if your sample that you start with, suppose we're titrating a weak acid with sodium hydroxide. At the endpoint, what will our pH be? Okay. And people are saying higher than 7. Why will the pH be higher than 7 if we start with a weak acid sample? So if we start with a weak acid sample, let's see where's the reaction. We start with a weak acid sample. At the endpoint, what will have happened to that sample? What do we convert it to? The conjugate base of the weak acid, right? What do we know about the reactivity of the conjugate base of a weak acid? Does it have some base level reactivity with water? Okay, so we essentially just made a solution of a weak base, right? And what happens to the pH of a solution of a weak base? What we make is a slightly basic solution. That base reacts with water to produce what? Some hydroxide ion. So what happens to the pH? It goes up. Yeah. Okay. Let me just also point out, what do we have present in solution halfway to the equivalence? When we start, we have all of our HA acid, right? At the equivalence point, what do we have? All conjugate base. What do we have in between? We have half of our starting acid and half of our conjugate base. And it turns out that if you read the pH halfway, that gives you the pKa of the weak acid. We'll talk about why that is next time. Okay, so if you do a titration curve like this, you could figure out the concentration of the acid. Could you also figure out the Ka of the acid? And from that, could you speculate about what the acid actually was? Yeah, you could. We'll come back to that. Okay. Can you do the same calculation, assuming that a weak base is in the solution and you're titrating with a strong acid? Yeah, you can. Sorry to do this to you. It's much more fun when you can stop and get through. Okay, one more thing. Up to now, we've talked about monoprotic acids, which means what? There's one proton that gets donated. Okay, but there are a whole bunch of acids formula with more than one proton. So remember we said from the formula, if it's H and then something else like HF or HSO4 minus, or there's an H at the beginning of the formula, chances are it's an acid, right? Okay, look at these. Ascorbic acid, H2. Carbonic acid, H2. Citric acid, H3. H2SO3, H2SO4, all of those. If you see this H2 and it's not a methyl group at the beginning, that's your clue that it's an acid, but it has more than one proton. Okay, let me draw a formula for these because I think that will be helpful to you to visualize what's happening. The thing about a polyprotic acid is that all of the protons have the same reactivity. So suppose I'm writing Here's the Lewis structure for sulfuric acid. How many acidic protons do we have? 2. Is one more acidic than the other? They're the same. But this is what happens in a polyprotic acid. One of them is going to get pulled off first, right? Okay, when that one gets pulled off, it changes the acidity of the one that's left. Because when you pull off the first one to form the first conjugate base, what happens to how hard it is to pull the second one off?
Easier.
So this has a -1 charge. If I pull off this second proton, what does the next one have? It's going to have a -2 charge. Okay. So go back to here. Even though these protons are chemically equivalent when the reaction starts, you pull one off, and the next one is harder to pull off. Have a different equilibrium constant for each subsequent proton. Call them Ka1, Ka2, Ka3. Obviously, which K value corresponds to the first one pulled off? K1. Yeah. Okay. What happens to the magnitude of Ka2? The Ka value for pulling the second proton off becomes a lot smaller. Like 10 to the 5th or 10 to the 6th. Smaller. It's a big difference. Okay, so what does that tell you about once you pull the first one off, how hard is it to pull the second one off? A lot harder. Okay. Is that surprising or not? Look at the structures of the conjugate bases that form after we pull off the first one proton. Okay, so if we do sulfuric acid here, when the first proton comes off, is that pulling off a proton as a strong acid or a weak acid? K value is about 10 to the 3rd. So the first proton, that's a strong acid. Now we have to pull a proton off of something that's already negatively charged, and what do we form? Something with a -2 charge. So every subsequent proton we pull off, what happens to the stability of the conjugate base that we form? It becomes less stable. So what does that tell us about the acidity of the proton we had to pull off? It gets less acidic. So every time you pull a proton off, it gets harder to pull the next proton off, and the Ka values go down. Now, there are 2 categories of polyprotic acids I want you to notice. Notice that nearly all of these polyprotic acids that I'm showing you here, they're weak acids. The first proton being pulled off corresponds to deprotonation of a weak acid, right? How can I tell from that figure? JC, what data is on there that tells you that?
The 10 to the negative parameter.
Yeah, these are all approximate Ka values. And they all have negative exponents, so that's all a weak acid. There's one exception, and that's sulfuric acid. That's actually the only polyprotic acid I know of where the first proton is a strong one. Strong acid. Okay. Can you explain the difference in the Ka values? Why would the second proton be so much harder to pull off than the first one?
Yeah.
There's 2 ways to explain it. So one way to say it is every time you pull a proton off, you form something with a more negative charge, which is going to be less stable. So each subsequent deprotonation creates a less stable conjugate base, which means that the precursor acid was weaker. The other way to say it, that's a little easier to conceptualize, is to say, every time you pull a proton off, you're pulling a proton off from something that has a negative charge, right? It's harder to pull a proton, a positive proton, away from something that already has a negative charge. So every time you do that, you're pulling a proton away from something with a greater negative charge. It's harder to do. Reading quiz question. Someone asked me, are monoprotic or polyprotic acids stronger? Is that a fair division? We don't typically rank acids using whether they're monoprotic or polyprotic. How do we rank them in terms of acidity? We just look at the Ka value and figure it out that way. Okay, you're titrating a polyprotic acid. What's it going to look like? Okay, every proton has its own equivalence point. So you start with a polyprotic acid sample. First, you pull off one proton. There's the equivalence point. If you keep titrating, you pull off another proton. And a second equivalence point. Okay. Is this a diprotic or a polyprotic acid? Sorry, diprotic or triprotic? How many equivalence points do we have? 2. So how many protons go? 2. So it's a diprotic acid. Okay, how would you use the titration curve to calculate your sample concentration? You have more than one choice here. This equivalence point at this volume that corresponds to the first equivalence point. Have you added exactly the same number of moles of sodium hydroxide as were the sample? Okay, this equivalence point. We have to add exactly twice as much volume to get to the second equivalence point. Does that mean that we've added exactly twice as many moles of the sample? It does actually. Twice. Okay. Essentially, the calculations are identical, but we have to correct for the difference in stoichiometry depending on whether we're titrating to the first equivalence point or the second equivalence point. So you know the point in a stoichiometric calculation where you say, I know how many moles of starting material I have, and I need twice as many moles of whatever else they're asking for, where you do a calculation that corrects for the stoichiometric ratio. You have to do that here. Okay, how do you know you're not titrating a base with an acid here? P starts low. Yeah. Okay. What do we do with titration here? First problem is to figure out what reaction we're actually carrying out in the titration. So this one says we start with H2SO4, titrating with sodium hydroxide, and then it uses this word to react completely with the acid solution. What's that code for? How many protons could we pull off? H2SO4 is a diprotic acid. We have 2 different protons we can pull off. If we're reacting it completely, what does that mean? We pull both of them off. Okay, so the reaction here is H2SO4 becoming sulfate ion. We're going to go to 2 equivalence points, so we need 2 equivalents of sodium hydroxide to get the product. Okay, if the problem said react to the first end point, what reaction would you do? Just have 1 form HSO4 moles. So your trick here is that you have to read carefully to figure out what the reactions that we're talking about. Once we know that it's reacted completely, we know it takes 2 moles of sodium hydroxide for every 1 mole of acid because we're reacting with both of those protons. Okay, how do we set up the problem? We figure out the concentration we want, the moles of sample divided by the liters of the sample, right? So let's calculate the number of moles of sample. It's the same as the number of moles of sodium hydroxide to start with. Calculate the concentration of sodium hydroxide times the volume of sodium hydroxide. That gives us the number of moles of sodium hydroxide, right? But now the stoichiometric ratio isn't the same for the sodium hydroxide and our starting acid, and we have to correct for that. So we say there's 1 mole of H2SO4 for every 2 moles of sodium hydroxide, right? That gives you the number of moles of acid. If it wants the concentration of the acid, what do? Divided by the number of liters. Okay, on the reading quiz, we did a similar titration, except what do we know about the base? So this one, we were titrating a base as our sample with hydrochloric acid as our titrant, right? But there are two hydroxides in the base, so it's essentially the basic version of a diprotic acid. I don't even know what word that would. Did anyone come up with that language when you're reading? Same kind of problem, you do it the same way. Except the barium hydroxide is your sample and the HCl is your acid.
Do those kinds of bases experience
Yeah, they do.
They do.
So it acts just like a polyprotic acid, except you're titrating first direct. Okay, equilibrium problems with polyprotic acid. Not as hard as it sounds. And the reason that it's not as hard as it sounds is most of those acids, the first association is weak, right? So take phosphoric acid. First pH value is 7 times 10 to the minus third. When you set up your rice table, how much product are you going to get? Here, let me show it to you. Hydrogen carbonate. K value is small. There's 2 protons. Each of the proton has a K value, Ka1 and Ka2. The first ionization, if you mix it with water, what's going to happen is the carbonic acid is going to form H3O plus the conjugate base, right? How much of conjugate base are you going to make? These X. It's not very big. Okay. And whatever amount of this carbonic acid that we form, this small quantity, some of that can go on to donate an additional proton to water, right? How much are we going to donate? This second reaction, the carbonic acid reacting to form carbonate ion, is an even smaller K value. Okay. So if let's just solve the amount of bicarbonate that we're going to form here from the first ionization. How much do we have? Not very much, right? If we start with that amount of material and set up a rice table and solve for how much that dissociates with the second Ka value, which is 5 times 10 to the minus 11, are we going to have enough to care about? No. So what do we assume? We just do the first ionization and pretend the other ones don't matter, because they don't. They don't make enough of a difference to matter. So this looks really difficult, right? Because it's a polyprotic acid. Is it any different than the equilibrium calculations you've already done with the monoprotic acid? Okay. What about sulfuric acid? Sulfuric acid happened. This next time, let me just say, sulfuric acid is a strong acid, right? So when you add 0.3 moles per liter sulfuric acid, what are you going to get? Water. 0.3 molar hydronium plus 0.3 molar hydrogen sulfate. But the hydrogen sulfate, can it react with water? Yeah, and it will. So you have to set up a rice table calculation where you're saying how much will hydrogen sulfate react with water? How much you have? It's a strong acid, but here's a trick. You also have a bunch of hydronium already present from the first dissociation. So you have to set up a rice table calculation. Go over those, come to office hours, answer the questions for yourself. I promise this isn't as hard as it sounds once you wade through. If you need help going over all of these, thanks for being patient and so.
I read this last sentence.
Yeah. But you.
Sorry. I never done it.
Yeah, I'm gonna just look at my test real quick.
Maybe I shouldn't let you.
I can roll with that. Okay, yeah. And I'm still in the consideration.
So because it's after. Oh,
So,
perfect.
it's next.
Okay, so I should send this.
And I kind of figure out like, I don't know, I still have a lot of the resources and I tried to practice this.
Well, and it's a different kind of thing, right? And so some students start it, and it takes them a little longer to figure out. To jettison their old learning style and learn a new one.
Yeah.
Because that's not trivial.
And I had a similar experience in high school. Withdraw from like my algebra 2 class, but then I ended up coming back and I got like a B+ in algebra 2.
Yeah.
So anyway, I thought I
I
was just
don't
like,
think it's a failure, and if you need someone to feel like you have permission to do it, I give you permission to assess and say. Like.
Yeah.
Because you are kind of. Catch up at a time. when It's just all of a sudden, right? So,
well,
you don't wanna-
I'll let you know. I mean, I think it's fine.
How are you doing?
And I never know whether to do more at the beginning of class or less.
What do you mean?
Today I did more, and then we were the whole rest of the class.
Even more?
Well, we did more review. A
Oh,
lot of people weren't really,
I thought it was helpful.
I thought it was super helpful.
well, people weren't present, even, think about the day after an exam.
Mhm.
Is that even when people are physically present, there's just not as much skin in the game, kind of,
Yeah.
like it just happens. So. No criticism, just.
Sort of.
That's also true in 105 today.
I'm sure you went over this on Tuesday and I was not here. Number 5
Number 5.
on the test, I was told not to do
Yes,
it.
because it's actually number 19, but the figure you need is on number 19 and not number 5. I don't know how I missed that.
Okay,
Double
so,
question.
so I assume like on the. It's marked wrong.
Well, it wouldn't have been marked wrong, but you wouldn't necessarily know how to do it. I will fix that for you.
Okay. I was just confused if, I assume that was not a graded question.
So this is what happened. I rearranged the questions.
Mhm.
Normally I cut and paste, and apparently that time I copied and pasted and didn't realize that it still showed up in the earlier place.
Yeah.
And I had this concern that I'd seen that problem and it didn't have the figure next to it. I looked through the test and there was the problem and it had the figure next to it. So I said, oh, all good. But it showed up earlier and I didn't notice. Not supposed to happen, and sorry to put you through that.
Oh, no, that's okay.
I have a question. So we don't do this on future tests. What is shorthand?
I would like to be able to say, this is the approach that you use, this is the equation, this is where you put your numbers. And I can't really do that based on what you did.
Okay.
So There's only one more test where this is gonna show up for you, because we only have one more that even has a short answer section. If someone says, here's the equation and writes it out, and then puts in the numbers in the right place with the units in the right place,
Mhm.
even if they get the wrong answer, I can say, they knew what to do.
Yeah.
They just made a mistake, and then they get a bunch of points back.
Mhm.
And I couldn't do that for you here because it
Yeah, 'cause I
wasn't
just feel
there.
like I had all the calculations and stuff in my head. And I'm like, this is it.
So, couple of problems with that, other than that I can't give you partial credit.
Yeah.
The other problem is it's easy to make mistakes that way.
Yeah.
And if you set this up with all your units and
Mhm.
cancel all your units and do that for everything.
Yeah.
You find problems that way.
Mhm.
So it's just a little, taking the time to write it out gives you one extra chance to correct any mistakes.
And then, what was it? So how do you do this problem?
Okay, so there are two equilibria, right? It's common ion
Yeah.
effect problem. This is the equilibrium it asked about, right?
Mhm.
But you already have 2.0 molar A plus other, so the equilibrium here is what you started with plus what you add,
That is 2 plus
2 plus x
x. And then,
times x equals 21.7.
oh, it's equal to 21.7.
Because this, the 21.7 applies to this equilibrium, right?
Okay.
So the KSB still governs this, but the common ion influences it because it changes the concentration of K plus that you have.
So is it 2 plus x times x equals
Equals the KSB.
21.7?
Yep. Yes.
Because I was like, I understand what's happening. I
We
just have no
did
idea.
some
what-
like this and we did one in class,
Yeah.
but I think people were kind of playing catch up and didn't quite bring their understanding of that thing that we did at the end. But, that's essentially what we're doing in acid base too, right? If you have the common ion, it shows up in your equilibrium line. See what I'm doing here. Okay.
So the next midterm, that'll be our last written response. And then the next fall.
Unless I decide to. Then I have to. give them back. And the truth is, at that stage of the semester, any delay in me grading it means you don't get a chance to go over it before the final.
True, that's true.
Because you take the test on a weekend, we have one more lecture, and then you're done. Insane.
Yeah.
Oh my gosh.
So multiple choice has some advantages,
I like multiple choice.
other than the fact that students are less
Because
stressed.
I always miss points on like, I didn't put a J for joules. They're like, yeah.
So if you get in the habit of doing all that in your homework, it will help. It's supposed to be that you have an opportunity to get partial credit as well, but that didn't help you very much.
No, I think that's like where almost all my missed points came from. Like, there's no joules, there's none of this. Like, what are you even doing right here?
And that's frustrating, but on the other hand, the language. Know that you knew what it was, but if you don't write it, then you're not expressing the meaning. Does that make sense?
Yeah, exactly.
It always hurts me when I'm grading.
Next test, I'm gonna write every single thing. Don't you worry.
Good, that's perfect.
You are now 2 weeks away